Gang, back in the stew. Win, 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 win. How can I lose? What's up, guys? It's Friday. And we're going to do problem 396. Rotate function. 369. One more time. Get low. Yeah, so let's go ahead and get right into it. So, you are given an integer array nums of length n. Okay? Assume array k can be the array obtained by rotating nums by k position clockwise. Or for you, I don't know if it's reversed. We define the rotation function f on nums as follows. F of k equals array k 0 plus 1, array k 1 times 1, plus m. Okay. Return the maximum value of f0, f1, and f of n minus 1. All right, so sometimes when you read these descriptions, if you don't have a strong intuitive math oriented brain, you might be like, what the heck am I looking at? So don't let that deter you from trying this problem. Just look at an example. So 4, 3, 2, 6. So the first thing we do is we multiply 0 by 4, 1 by 3, 2 by 2, and 3 by 6. Okay, and then we do 0 times 6, 1 times 4, 2 times 3. So you just have the sliding product sum, right? So for this example, you have nums equals a 4, a 3, a 2, a 6. And then what you're going to do is use this other, I guess you could think of it as an array, I don't know, right? Where you multiply these things out, right? So you do 0 times 4 plus 1 times 3 plus 2 times 2 plus 3 times 6. And then you rotate this like this. Now, of course, there's an offset here. So that would mean that if we just copied it again, that way you could see how everything's in every spot. So now you do 0 times 6 plus 1 times 4, right? 0 times 6 plus 1 times 4 plus 2 times 3 plus 3 times 2. 2 times 3 plus 3 plus 2. And then you move over again, right? Now you do 0 times 2 plus 1 times 6 plus 2 times 4. And you do that over and over again until you get the, until you do it for everything, right? So you would do it for this, and this, and this, and this. Do it for all of them, and then return the maximum answer that you get. So there's a very obvious n squared solution, right? You would literally just try each one, right? You would do this sum, shift over, do it again, shift over, do it again, shift over, do it again, return the maximum. That is n squared runtime, right? Because you could think of each of these indexes as a pivot, right? So you'd have to do it once where 0 is, right? You do it once where 0 is at 4. You do it once where 0 is at 6. You do it once where 0 is at 2. You do it once where 0 is at 3. And you do it once where 0 is at that's it. Sorry. Right? And so for each number, you have to do n operations, right? Because you need to compare, you need to do a multiplication at each index, right? Because 0 times the first thing, 1 times the second thing, 2 times the third thing, so on and so forth. So that'd be an n squared algorithm, right? Look at each number. For each number, you have to do n operations to find the sum. So that's n for n squared. Make enough sense? Okay. Now, the solution to this is something that it just kind of hits you or it doesn't. And what might work is playing around with the numbers a little bit to get to an n time algorithm. I kind of realized now something that I've started to notice on Leetcode, and maybe depending on when you do the problem, you can use this information to indicate what the runtime complexity can or can't be, right? So I thought maybe the n squared solution's fine. You know, maybe that's just what this problem has, and you just literally follow through and do exactly what it says and return the answer. But when you look at n here, right, where we said that n is an n squared algorithm and n is less than or equal to 10 to the 5, that means that n squared would be 10 to the 10, right? So that's a lot of zeros after a 1. So that's probably too many operations, and it's going to give you a time limit TLE. So how do we approach this problem and get it faster, right? Maybe log n would probably be acceptable. N would be ideal. Well, the way that I got to my solution is by thinking about what this actually means and how we can reuse information every time we compute. So when we find this first sum, right, we do 0 times 4 plus 1 times 3 plus 2 times 2 plus 3 times 6. Okay? And then when we shift over by 1, right? So this is our first sum. Now let's look at our second one. What would our second one be? Well, we would shift over 0, 1, 2, and 3, right? And we do 0 times 6 plus 1 times 4 plus 2 times 3 plus 3 times 2. So when we compare both of these, what kind of assertion can we make? Well, number 2, what is it in terms of number 1, right? What is number 2 in terms of number 1? Can we use number 1 and do something constant to get to number 2? Well, for number 2, let's reorder this in terms of the numbers and not like the indexes we're multiplying. If that doesn't make sense, what I'm basically saying is like, where do these things go? So everything's going to get shifted over 1. I'm talking in terms of... what I'm going to do here is just so it's a little clearer what I mean. So I'm just going to use the same colors so you can see what I'm talking about here. Let me do 1 times 4, 2 times 3, 3 times 2, 0 times 6. Okay. Okay. So this is also number 2 in terms of number 1, right? With sums, you can do them in any order. So I just reordered them so that the 4s with the 4, 3s with the 3, 2s with the 2, 6s with the 6. Well, in terms of 1, right, we add in, there's an 1 additional 4. There's 1 additional 3. There's 1 additional 2, and there's 3 less 6s. Does that make sense at all? Right? In 2 in terms of 1, well, we added an additional 4, we added an additional 3, and we added an additional 2, and we subtracted out the 6s, right? Because this number 2 rewritten, right, is also 0 times 4 plus 4 plus 1 times 3 plus 3 plus 2 times 2 plus 2 plus 3 times 6 minus 3 times 6. Right, this is literally the same thing, right? I pulled out a 4 and I said 0 times 4. I pulled out a 3 and said 1 times 3. Right, and this right here is 1. So number 2 can be rewritten as... See, this is why this problem is kind of bull, because it kind of reminds me of something you do in college, right? Where you're like, and then you do this, and then when you take the derivative and you reorient the space, you get into this sort of situation. Now you can take the derivative with respect to this differential, right? And then that's why this problem's kind of silly. But if you encounter it, it's kind of a fun exercise. It reminds you of an easier time in life. So that's number 1. Right, and then the additional factors, we have plus 4, plus 3, plus 2, minus 3 times 6. Okay. Now, if we did some interesting things. Now, the assertion I'm going to make is just kind of like an inductive reasoning, and I'm going to just state it, and you can think about it, think it through, right? Because I could start this pivot anywhere and move it over to the left whenever I want. Like by 1, I could have started it in this position, right? And then made the same argument when I moved it over 1. So what I'm basically saying by that is like, this works for any adjustment by 1, right? Number 2 is always equal to number 1 plus something. Okay? So what can we say about these terms here? Well, what if we called this number 1 plus 4 plus 3 plus 2 plus 6 minus 4 times 6? Right? This is identical, right? Because now I've subtracted an additional 6, so I have to add an additional 6 to get back to where I need to be. And then what is this? Well, this is just the sum of the numbers in our system. So if we call S equals the sum of the array, right? So that's number 1 plus the sum of the array. And we'll pre-compute this so we don't have to compute it over and over again. Minus and then what's 4? Well, 4 is the length of the array, minus the length of the array times. So how do we get 6? Well, our pivot point is now 6. So whatever index we're at, that's now the thing we're going to subtract out from the previous solution, right? Because in the previous solution, the 6 was at the highest point. Now it's at the lowest point, right? Now it's associated with 0. So now you subtract out that from the previous solution times the array at the pivot. So that means number 2 equals that, right? So to find number 1, to find this information, you calculate this idea 1 time. That takes n time, right? Because there's n items, then you do the n multiplication. And do multiplication for each item, that's n. Taking this, you can calculate that just 1 time before, so you don't have to do it every single time you find an additional system. So this is a constant operation, if you think about it as, well, the thing that I found before, right? So this takes n time, this takes n time, but for each of these relationships, this takes constant time, this takes constant time, this is a constant operation, this is a constant operation. So finding this whole system is constant. And you could do that for any such pivot point, right? So that means you only have to do this operation n times, and each operation is constant. So this is an n time algorithm, okay? So with that, let's go ahead and try to solve the problem using the Leetcode. So we'll call S the sum. So S equals sum of nums, right? And then I said we need to calculate number 1, right? Let's have our sol equals 0, so we don't know what our best solution is. Okay, well, nums could be negative, so don't want to do that, actually. So let's first find our number 1. We'll call that our dynamic programming solution, D. And that'll be what? How do you find that? Well, it's the sum of the element times its index for each index and element and enumerate nums. Right, so this will take the element 4 and multiply by 0, and then add in 3 and multiply by 1, and so on and so forth. All right, and then we'll look at each pivot point after. Now notice in our system, the next pivot point for number 2 was 6, right? Because we moved backwards, and that's just because that's the way it worked here. I'm guessing you could do it the other way, but your recurrence relationship would change, I guess, a little bit. So let's just go backwards through the array since we did it like this. I'm trying to think about if it would be the same thing in the other direction, but interviews are short usually, so don't try to think about how something else could happen while you're in the middle of going down one road. Okay, so we'll look at each pivot point in range. We'll start at the length of nums minus 1, so it'll be the last index. We'll go all the way to 0, and of course we're going in the reverse direction. So our solution is then, well, So how do we get our next D value? Remember, this is number 1. This will be our number 2. We'll say, well, D equals, what was our formula? I already forgot. We take number 1, so we take what it was before. So we could do plus equal. So D equals D. So D equals You don't want to look at my code. D equals D plus the sum of the array minus the length of the array times the pivot point. Okay. So D equals D plus the sum of the array, which is S, right? A constant operation because we pre-computed it, minus the length of the array, which is nums, times the pivot point, the number at the pivot point. So that'll give you the next sum, and then you can just see if that's a better solution. My variable names today are really bad. Sorry. And then when you're done, you just return the solution. And with that, we are finished. Hey, and So what's the runtime of this? First and foremost, I want to say this solution is really ugly. But what are you gonna do? You know, what you gonna do about it? It's an ugly solution, but it works. Okay, so this takes n time, right? Because you have to look at each number to sum them. This takes n time because you have to look at each number and sum them. This is a constant operation. This is going to take n time because you have to look at each number as a pivot. This is a constant observation, right? Because you've already pre-computed this, so this is constant. Finding the length of something, that's just catch, so that's constant. And finding the numbers of pivot, multiplying it, that's constant. So this is a constant operation. Comparing two things and finding the max, the constant operation. So for n operations, you do something constant. So this is O of n time. In terms of space, well, we're not really saving anything, right? We save a constant for the sum of m's. We save a constant for the first value of d, a constant for the mesh solution. So this is as good as it gets, right? So for time complexity, we have O of n. And for space complexity, it's O of 1 because it's O constant. However you want to look at that. All right, guys. Gang, gang, gang. Back in the stoop. Peace.